Well, good morning, ladies. Today's Tuesday, the 21st of July. So today we're going to finish up lecture 7, and I'll do the second, I'll review the second half of the lecture 7 homework, or the homework 7 practice homework. I have gotten emails from quite a number of you all about the survey. So I'll give you until tonight if you haven't sent an email yet. That is part of your grade for your participation on the project. So if you have not yet sent me an email about the survey, please do so, letting me know your feedback, if you think it looks okay, if you think anything needs to be changed, if you have suggestions. I appreciate the input that I've received. If you see any mistakes, anything like that. So some of the input's been really good. I'm not sure it's going to be feasible for us to utilize just because it makes it a little bit more complicated, but it's still really good feedback, the feedback that I've received. Several of you have mentioned adding some more variables, that kind of thing, which, like I said, if we were doing, if we had a little bit longer, it would be a really great idea to add those, because there is a lot of error when you don't have additional variables. But I want to, for the sake of keeping it streamlined, I may not be adding any more variables to the project. But I do appreciate your input. It shows that you put thought into it, and it's valid suggestions for what we could add to make the study better. So today we're going to finish up lecture 7. So I think I'm going to go ahead and get started with that. So we'll start with a screen share of the outline. So let me do that. Okay. Okay, so the outline for chapter, or for lecture 7, if you'll remember from yesterday, we started by talking about probability, just probability being the odds that an event will occur, and those odds are between 0 and 1. 1 would be 100% chance it's going to occur, and 0 would be 0% chance it's going to occur. So most of the time it's between those. And that's all figured based on the ways a specific event could occur, and then the total ways associated for that likely event to occur. And so I gave examples of, like, you'd have a 1 out of 6 chance to roll a 6 on a dice, or to roll a 4 on a dice. So it's the whole idea that probability gives us confidence around how likely it is for 2 groups to be different, or two groups to be the same, or a raw score to be different from the group, the sample that it's in. So that's how we apply that. This is the odds that a given score may occur, can be directly calculated by looking at how it falls on that Z distribution, where the mean is 0 and the standard deviation is 1. So the odds that that given sample score can be directly calculated for sample means also by using what's called a student t distribution. It's very similar to the to what we were doing with the Z distribution. You look at the mean of the means, and then you use standard error as the standard deviation. So you guys have all done that. And we've talked about the test of significance. So remember that small p stands for the probability, and then you'll get a number, okay? It's usually, it is less than 1 because it's always between 0 and 1. And we can also look at that as a percentage, so we can move the decimal point 2 points. So for instance, if the p is equal to 0.001, that would be 1 out of 1,000 or 0.1%. Okay, so we can then look at the basis of a test of significance by looking at how much those samples vary. Okay, so when we measure statistics from one distribution with the other, if we have more than one sample, then we can look at the range, the normal range that these two statistics are in. And we know the normal range is going to be 2 standard deviations. So we kind of had already talked about that. So if it falls within 2 standard deviations, it's within 95% of the data. If it falls outside of that 95%, right, then it's considered different. Okay. So we talked about how to apply the test of significance by stating a hypothesis, either the null, where you say there's no difference, or the directional or alternative hypothesis, where you actually hypothesize a difference. You choose a significance level. We're going to be using a 95% significance level, which gives you a 5% alpha level. And then if we're looking at 2 groups, we're going to use a t-value. If we're looking at more than 2 groups, we're going to be using an f-value. And then if we're comparing our sample mean to the population mean, we're going to look at a z-value. Okay, so mostly in this class, we'll be doing t-values and f-ratios. Okay, so we've determined our alpha level. We're going to be using the 0.05 level. And then we determine whether it's a one-tailed or two-tailed test. A two-tailed test is when you're utilizing a null hypothesis. You're saying there's no difference. The one-tailed test is when you have an alternative or a directional hypothesis where you're saying, oh, it'll be significantly different. It'll be significantly higher or significantly lower. Okay, so it puts all the error on one end of the normal distribution. Then you do your inferential test, and then you can determine your t-value, your f-ratio, your z-value, and compare it to a critical value of those levels based on the number of subjects that you have. So this either comes from a table that you could find in your book on the internet, or Excel will do the comparison for you and give you the probability. So that's what we looked at yesterday in the homework. So once you know whether your calculated t-value is higher than your critical t-value, or if your p-value is less than 0.05, once you know that, you can tell whether there's a difference or not. So remember, for there to be a difference, the p-value has to be less than 0.05 or less than 5%, has to fall in that critical range. And then the t-value would have to be larger than the critical t. Okay? So we then talked about doing these tests, these inferential tests of significance. So if we only have 2 groups, so we only have 2 samples that we're going to compare, we're going to use, or 2 variables that we're going to compare, we're going to use a t-test. We're going to be using a t-test in order to determine or calculate a t-value, okay? So there's two different kinds of t-tests. There's an independent sample t-test and there's a dependent sample t-test. So the independent sample t-test, these are two separate groups with one variable measured, okay? Two separate groups with one measure variable. We could have men and women and we measure them on weight, or we can have college students and non-college students, and we measure them on their attitude about sexuality. But it's two separate groups, one measurement, okay? Okay, and for the dependent sample t-test, okay, so the independent is the between measure, two groups, one measure. The dependent sample t-test, this is one group with two measures. One group with two measures. So I could have men and I measure their weight pre and post. That's a within measurement with one group and two measures, and it's called the dependent. On Excel, they call it the paired t-test. Okay, but when you see it in the literature or in textbooks, you're going to see it as the dependent sample t-test. Okay. Okay, and then when we read those outcomes, we're always going to look at our t-value compared to our t-critical, and we're always going to look at our probability, okay, depending on whether we have a null hypothesis or an alternative or directional hypothesis. Okay, so today we're going to talk about using more than two groups. Okay, if you only have two groups, you're going to use the t-test. But if you have more than two groups, you can't use the t-test, okay? Because every time you do a t-test, there's 5% error, okay? We've got that 5% critical region, okay? So let's say we had three groups, group A, group B, group C, and we want to see if any of those are different from each other. Well, if we use t-tests, we'd have to do group A against group B, then we'd have to do group B against group C, and then we'd have to do group A against group C. So we'd end up doing three different t-tests. And what would happen is every single time we do a t-test, there's 5% error. Okay, every time we do a t-test, there's 5% error. So we would end up with 15% error if we did three t-tests. So we don't really want that. So instead, there's a test called an ANOVA, or an analysis of variance. So what it does is it takes into consideration all of the variables, because there might be some overlap between variables. So it takes into consideration all of the variables and it looks for differences, okay, among all three variables without increasing the error. So we can do one ANOVA and we'll still only have 5% error if we set a 5% alpha level or 95% confidence level. Okay, so the ANOVA allows us to look at more than two groups, so three or more groups. It also allows us to do a between and a within measure within the same test. Okay, so not only can it do three or more groups, but it can also test a between and a within. So, and that's called a factorial. It's not a simple ANOVA, but it's called a factorial. So you can look at the VO2 of men, women, and children. Okay, so three groups, and you can also look at before training, 1 month, and 6 months. So you could do a pre, a post 1, a post 2. So not only will the ANOVA, factorial ANOVA, look at the difference between men, women, and children, it will also look at the difference between the pre, post 1 and post 2, but then it will look at the combination, or what's called interaction. So it can look at men. It could do a within, so it can look at men pre, post 1, post 2. It can look at women pre, post 1, post 2, and children pre, post 1, post 2, post, Then it can also look at the difference at post, at pre, between men, women, and children. At post 1, between men, women, and children, and post 2, between men, women, and children, which those would be between measures, between 3 different groups. So it can do the between and the within on what's called a factorial ANOVA. So this would be considered a 2 by 3 factorial ANOVA. Okay, so it's looking at it again, like when we talked about regression and it being more 3-dimensional. This is the same thing. It looks at interaction, not just between 2 groups on one measure, or one group just 2 measures, which is just bivariate. It can actually look at this in a multi-dimensional way. Okay, so it's factorial. Okay, but you can also just do what's called a simple ANOVA, which is what we're going to be doing, because that's the only thing Excel can handle. In order to do a factorial ANOVA, you have to have a more robust or a stronger software program, something like SAS, the statistical analysis software, or SPSS. There's a Minitab. There's a bunch of different software that can run, that can do something a little bit more robust or a little bit more complicated. Okay, Excel can't do a factorial ANOVA, but it can do a simple ANOVA. So it could just look at, say, for instance, on men, it could look at the difference between pre, post 1, and post 2. Or it could look at the difference between men, women, and children on pre. Okay, so it can do either one if you're doing a simple ANOVA. They don't call them a between or a within when you're only doing a simple ANOVA. Okay, it's just straight called a simple ANOVA. Okay, so we're going to be doing, we'll actually be doing a simple ANOVA where it will look at 3, or it could look at more groups. It could be more than 3, but it will look at more than 2, 3 or more variables. Okay, so it's most commonly used with 3 or more. You could apply it to 2, but it doesn't make sense. If you're going to apply it to 2, you could just do a t-test. Okay, I already talked about factorial. Okay, so when we use an ANOVA, what it does is it looks at the variability between the groups. It compares group variance. Okay, so it compares the group variance to the within group variance. So it looks at the between and the within together. Like I said, it kind of does a mixed model. Okay, so when you look at the between group variance, that's the mean square. Okay, if it's equal to the within group variance, then there's no difference in the mean scores. So this will, what the ANOVA does is it calculates that to come up with an F ratio, an F statistic. So it calculates an inferential statistic that we can then compare to the F critical. Okay, to know if there's a difference somewhere among those groups. Okay, so I already kind of talked about this. Why would we do ANOVA versus multiple t-tests? Because it creates what's called family-wise error, or it creates a lot more error. Okay, so we have to protect against that. That way we can use an ANOVA. So we use the ANOVA. It provides greater power. We don't have to correct the alpha level. The only thing about ANOVA is that when the F ratio is larger than the F critical and the p-value is less than 0.05, we know there's a difference, but we don't know exactly where the difference is. Like we wouldn't know if it's between group A and B, between group B and C, or between group A and C. So we have to do what's called a post hoc test. So we would use this post hoc test to tell where the difference is. Okay? So when we use ANOVA, we assume that our observations are independent, that there's not a ton of correlation or a ton of overlap, okay? That they're normally distributed, that we have maybe some randomization in there. The variance of each group is equal. They're more homogeneous for variance. If those are all true, ANOVA will be very robust or very valid. It will have good internal validity. Okay, so if we have this measure of ANOVA, if we said there's no difference between the three groups, so let's say we have group 1, group 2, and group 3, it will calculate the F ratio, the F statistic. Then we'll determine if the calculated is the critical is exceeded by the calculated. So the calculated has to be larger than the critical F. Okay? And then we could also look at the p-value. Okay, so if we do have a p-value under 0.05 and our calculated F is larger than our critical F, this is what the outcome is going to look like. So let's say I have these three groups, and I want to see if there's a significant difference between them. Okay? Then this is what the outcome looks like. This is a single factor or a simple ANOVA. Okay? So I've got my three groups, 1, 2, and 3, with 9 observations each. It's going to give you the average of those. So the average for group 1 was 5.4, the average for group 2 was 2.7, and the average for group 3 was 10. Okay? Then you can see it does a between group and a within group. It calculates an F ratio. So here's my calculated F ratio, 50.55. Here's my critical F value, 3.4. So is 50.55 larger than 3.4? Absolutely, okay? So that means that there's a significant difference in there somewhere. My p-value is 2.49 e to the 09, which means there's 9 zeros in front of this 2. So decimal, 9 zeros, 2.49. Okay? Or, I'm sorry, I always say that wrong. There's actually 8 zeros because we just moved this 9 positions over. So we have to account for this 2. So if we move this 1, then there would be 8 more movements, so 8 zeros. So 8 zeros, 249. So that's way, 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 way less than 0.05. So we know the p-value shows that the chances of this occurring are very low, or the chances of this being wrong are very low. Okay, so we know that the p-value, it's way less than 5%. The chances that this occurs way less than 5%, okay? That there's not a difference. So there's a difference somewhere. The chances that these would all be the same is super low. Our F ratio is higher than our F critical. We know there's a difference somewhere. Now we could just look at this and say, well, for sure we know this probably is different from the 2, but we don't know if the 5's different from the 10, or we don't know the 5 and the 2 are different. So we have to do what's called a post hoc to tell where the difference is. Okay, we have to run a post hoc test. Okay, so when we use a post hoc test, this determines the probability that the difference exists between the multiple groups, but it tells you where the difference is. The post hoc tests will determine specifically where the difference is. So in this class, we're going to be using what's called the Tukey's test of honest significant difference. So it's called the Tukey HSD. It's commonly used to check differences, especially with simple ANOVAs, okay, or one factor ANOVAs. Because it can only be used when the groups are equal in size. Okay, once the ANOVA table has been generated, the Tukey formula provides that feedback as to whether there's a difference. Okay, so the Tukey's HSD, what it does is there's actually a formula to calculate the Tukey HSD. I'm not going to require you to calculate that. Okay, you could, because you can look at the degrees of freedom within, okay, and then you could look at the n minus the k. So if we go back and we look at these, we can look at the between and the within in order for us to determine what the Tukey HSD is. Okay, so the n is the number of observed in each group. We've got 3 groups, 9 observation, 27 total observations. So the number of groups, the K is 3. So we end up with, if we look at the degrees of freedom for that, we use this formula with the mean of the squares within being 2.407, and you can see that up here. 2.407, so it's the mean within, the n of 9, so you can see it calculated right there. Okay, so the degrees of freedom within, okay, times right here, times the square root of the mean within divided by the number. Okay, so you can see how that's calculated. I'm actually not going to require you to calculate it because the computer calculates it for you. I just want you to know that it's using the data. It's using the data about the degrees of freedom within, as well as the number of subjects and the number of groups, okay, to be able to calculate the Tukey HSD. So I will be giving you the Tukey HSD, so don't freak out about trying to memorize this. You don't have to memorize this, okay? But I calculated it there for you. So the Tukey HSD, the difference, the honest significant difference is 1.8255. So what this is calculating is the difference, the variability that has to happen between the groups, that it has to be at least 1.8255 or more, the difference, okay? So we have to see a difference of 1.8255 or more between these groups to say if they're different. So basically all you have to do is subtract them from each other. So if I take group 1 and I subtract group 2, that gives me 2.718. That's larger than the Tukey HSD, the Tukey's honest significant difference. So I know there's a significant difference between group 1 and 2 because the Tukey HSD is larger. I mean, the difference is larger than the Tukey HSD. Okay, then I can look at the difference between group 1 and group 3. So I can take 10, which was the mean of group 3, subtract the mean of group 1, and I get 4.56. That's also larger than the Tukey HSD. It's a larger difference, so I know they're different. And then I can look at the difference between group 3 and group 1. I'm sorry, group 3 and group 2. 10 minus the 2.77. I find out that the difference is 7.278. So what this is telling me is all 3 groups are significantly different from each other. Okay, so we knew there was a difference based on the F ratio and the p-value, but we weren't sure where the difference was. So then we calculated the Tukey's HSD, okay, by looking at the degrees of freedom, okay. I figured that all up for you. I looked at the degrees of freedom, determined that, and then I compared that, or I multiplied that by the square root of the mean square within divided by n, the number of observations, and that gave me a Tukey HSD of 1.8255, which I'll be giving you that on the quizzes or the test. I'll be telling you what the Tukey's HSD is. All I have to do then is subtract these from each other to see if their difference is greater than the honest significant difference. If it is, then I know there's a difference between those two groups. Okay? So that's ANOVA. ANOVA looks at 3 or more groups to see if there's a difference between them. Okay, it can do a simple variable, just one group with 3 variables or 3 groups on 1 variable. Or it can do a factorial where it does a between and a within. It can look between the groups and it can look within like a pre and a post, or a pre and a post and a post. Okay? If the F ratio calculated is larger than the critical F and the p-value is less than 0.05, we know there's a difference somewhere. We would have to use a Tukey HSD to see if there's a difference. Okay, now, if the p-value is larger than 0.05 and the calculated F ratio is smaller than the critical, then there's no difference. Then there's no reason to do a Tukey HSD. We don't need to know anything about the honest significant difference because there's no difference. The ANOVA is telling us right off the bat, there's not a difference between these 3 or more groups. Okay, so if your alpha level isn't below 0.05 and there's no significant difference, there's no reason to spend your time calculating the Tukey HSD. Okay, makes sense? Okay, so again, the ANOVA is looking for differences. Are groups different? The t-test is looking for differences. Are 2 groups different? Okay, are 2 variables different? Okay, the correlation is looking for a relationship. Are 2 variables related? And regression is looking for relationships and prediction. Okay, and multiple regression can look at more than 2 variables. Simple regression looks at 2 variables. And the regression is where you can calculate or determine the line of best fit. Okay, the equation y equals mx plus b, where y is your dependent variable, m is your slope, x is your independent variable, and b is your intercept. Okay, so those are the 4 inferential tests we've learned in this class, where we can actually make decisions. Oh, those 2 groups are different. Okay, oh, those 2 variables pre and post are different, or they're not different. Okay, we're making a decision. We're testing a hypothesis. Or, oh, those 2 variables have a strong relationship. It's significant. And we can use it for a prediction by using regression. Okay, and we can make some decisions. We could predict things. Okay, we could see if variables were related. We could come up with some more research questions. Okay, so those are the 4 inferential tests you've used or learned. And then the statistics, the inferential statistics you've learned about are the, for correlation, it's the Spearman R. For regression, you're looking at the F ratio and you're doing a regression equation. Okay, for t-test, you're looking at the t-value. For ANOVA, you're also looking at the F ratio. Okay, so those are the inferential statistics that you've learned about. Okay, so the last concept I want to talk about is type 1 and type 2 error. Okay, so error, we already know that error occurs. Okay, error is in measurement. When we do research, we're going to have error. Okay, and we've already talked about the standard error, okay, that's how much the standard error is how much sample means vary from the mean of means, okay, on a t-distribution. Okay, so we're going to talk about type 1 versus type 2 error, okay? So type 1 error, this is when we say there's a difference, okay, but there actually isn't. So we reject the null. We say, if the null hypothesis says there's no difference, we reject that and we say, yeah, there's a difference. Okay, but there actually isn't a difference. So you want to write that down, okay? Type 1 error is when we say there's a difference between two groups, but there isn't. In reality, there is no difference between those groups. Okay, this is referred to as a false positive finding. Okay? So when we do, when we use the 0.05 and the 0.01, we're trying to control alpha level. The more stringent the alpha level we adopt, the more the more we reduce type 1 error. Okay? So type 1 error, when we say there's a difference, but there actually isn't. Okay? So what would happen, just for me to show you an example, if I have a normal curve, okay, so I've got this normal curve, and I've got my 95%, I've got my two, actually I'll just put the third one too. I've got my 2 standard deviations, but I know that this is my 95%, and that's what I'm using. So if I had a score that fell outside the second standard deviation, and I said, oh, that's different because it falls outside the second standard deviation. So that actually is from a different population. You know, I'm saying there's a difference, but let's say in reality there wasn't a difference, then I'm committing type 1 error. The way I could correct or reduce type 1 error is I could use a more stringent alpha level. So I could decide in order to make it, oops, I don't know what happened to my curve. Okay, so in order to make it less likely that I commit type 1 error, I could decide to use the 99% alpha level, okay, a more stringent. Now, if I'm at the 99%, and this is where my sample fell, is that considered different at the 99%? I can't get my light good. Okay, is that considered different at the 99%? Does this fall outside the third standard deviation? No. So if we were using the 99th% confidence, this score would not be considered different. Okay? Are you guys seeing that? Okay, so one more time. If we've got our normal curve, and we're only using the 95th, we're only going out 2 standard deviations. If a score fell here, it would be considered different. If it's not really different, the way we could have controlled for that is to use the 99th. If I used a 0.01 alpha level, then that score would not be considered different. Okay, so there's some research. We would want to be really careful not to make to say there's a difference when there's not. okay? So let's say we're testing a drug, or let's say we're testing for a COVID vaccine, okay? And we're using the 0.05, and we say like, oh, this worked. There's a difference between the people that got the vaccine and the people that didn't get the vaccine. Okay, and they fell, this is where they fell right here, and we're saying there's a difference. But then we start using the vaccine and people keep getting COVID, and we find out that maybe that was a false positive. You know, maybe we thought there was a difference and there really wasn't. So in medical research like that, where we can't afford to make a false positive, we would use a more stringent alpha level. Okay? We would use a more stringent alpha level. We'd be more willing to make a mistake in saying, and we might be willing to make more type 2 error, which is where you say there's no difference when there really is. Okay? Because it's just, these are people's lives. You know, we don't want to make a mistake. Where if we're doing research about what, you know, strength training routine makes you, you know, works the best to make you stronger, you know, nobody's lives are at risk here. We want to make sure we're picking up on any differences that might occur. So in social research, we're a lot more willing to make type 1 error. We're a lot more willing to say that there's a difference when there really wasn't, because there's not as much on the line. Okay? And we want to pick up where the differences are. We want to see where the difference might occur for some people. Okay? So type 1 error, we say there's a difference, there really isn't. We control it by using a more stringent alpha level. So we'd move from 0.05 to 0.01. Okay? Okay, type 2 error, this is where we say there's no difference, but there actually is. Okay, so we say there's no difference, but there actually is a difference. Okay, this is referred to as a false negative. Okay, we say there's no difference, but there actually is a difference. Okay, the way we control for this is to increase our sample size. So the larger the sample, the more power we're going to have. We're going to have a better shot picking up where the differences are. Okay, so the larger our sample is, the more power we're going to have. So our power increases as our sample size increases. Okay, so this is called the power of the design. So if I have a really, really small sample size, I'm probably going to commit type 2 error. Okay, I might not be able to see where the differences are because I just don't have enough people in my sample to pick up where the differences are. Okay, so that's why we need to have good external validity, large sample size to control for type 2 error. So we don't make the mistake of finding a false negative, saying there's no difference when there actually is a difference. Okay, so the larger you can get your sample size, the better off you are, and you'll be doing a good job controlling type 2 error. And there's actually a calculation you can use to calculate what power you need in order to detect differences, and it will give you an idea about what your sample size needs to be. And that's all based on how many variables you're looking at. Okay, so it's a calculate. I'm not going to make you, we're not going to do it in this class, but I just want you guys to know that, like, if you're doing research, you can you can get online and say ask to calculate beta or how to calculate power, and then you can put your information in and it will tell you, you're going to need this many subjects in your sample in order to have good enough power to pick up on the differences. Okay? So you need to know the difference between type 1 and type 2 error. Once again, type 1 error, this is a false positive. This is where you say there's a difference, but there actually is not a difference. Okay, you're making a false positive. Okay, the way you control for this is to use a more stringent alpha level. This would be important when you can't afford to make a mistake by saying, yeah, there's a difference when there actually wasn't. So it would mean, when I say afford, it might be you don't want to spend a ton of money on something that doesn't work. You thought it worked because you thought there was a difference, but it doesn't really work. Okay, and you don't want to spend a bunch of money on it, or you wouldn't want to risk people's lives. Okay, so that's type 1 error, more stringent alpha level. Type 2 error, this is where you don't pick up on the differences, right? You say there's no difference, but there actually is a difference. The way you control for that is to increase your power by increasing your sample size. Increasing your sample size. The larger your sample size, you're able to better control type 2 error. Okay. Questions about ANOVA or error, type 1 or type 2 error? Okay. So we can take a small break while I pull up practice homework 7, and we can do the second part of it. Okay, so if you want to stand up, take a stretch, get a drink of water. Okay. Okay, just as a quick review from yesterday, remember yesterday we were looking at t-tests. I'd given you this data that Dr. Dallum and I had collected on mean arterial pressure, blood pressure, and we had asked some questions in the homework. Question 1 was just what was the mean of the whole group, pre versus and post. So we just ran some descriptive statistics to find out that the mean for pre was 99.47, the mean for post was 100.24. Then question number 2 asked what was there a difference on the pressure pre to post in the whole group? So we had one group with 2 measures, a within measure. So we used the t-test paired for 2 sample means. And we found out that the mean at pre, we already knew this because we ran it before, was the 99.47, and the mean at post was 100.24. And I'm just going to use the null hypothesis for all of these. So we said there was not going to be any difference. So it was a 2-tailed test. So we came down and we looked at, we saw that the calculated t statistic was 0.75. That was smaller than the critical T of 1.99. So that tells us there's no difference. If the T calculated is smaller than the T critical, there's no difference. If the T calculated would have been larger than the T critical, then we could have said there was a difference. Okay, but in this case, there's no difference. We can also double check that by looking at the probability level for the two-tailed, since I had a null hypothesis. We find that the probability is 45%. That is not less than 5%. That is not less than the 0.05. So there's no difference. So in this case, I would accept my null hypothesis. There's no difference. Okay. Question 3, we sorted them by gender. So we wanted to look at men and women at the before measure. So at pre-test, we looked at them. Here's their means. We set a null hypothesis and said there was no difference. I'm going to head down to my two-tailed test. I see that my calculated T statistic was a 1.08. It was not larger than the critical. So it tells me there's no difference. I double check that with my probability level of 0.28. That is not smaller than 0.05. So I know there's no difference between men and women at pre on the blood pressure. So I would accept my null hypothesis. Okay, we go to the second half of that question. We looked at post. Okay, let's say I decided based on the data, no, let's just say I'm still at the null. I just want to stay at the null here. I'm going to say there's no difference between men and women. Okay, I go down, I see the T calculated is 1.31. It is not larger than 1.99. I look at my probability of 19% or 0.19. That is not smaller than 0.05 or 5%. So still, there's no difference. Okay, so I accept my null hypothesis. Now, question number 4 asked me to look at the 3 groups. I divided these, I sorted them, right? So I did a sort so I could get the group, the one-on-one group, and then the passive group. And then I looked at the pressures pre to post in each group, okay? So that's still a within. Oh, I forgot to say on question number 2, I was looking at, question number 3, I was looking at men versus women on one measure, the before. So I used the 2 sample assuming equal variances. Okay, it was 2 separate groups, 1 measure before, pre. Okay, same on the post. 2 separate groups, 1 measure, post, the after. Okay, so I also here use the t-test 2 samples, assuming equal variances, 2 samples. Okay, so on question 4, I'm going to do t-test for the before group, pre to post. Okay, the group, and I'm going to look pre to post. Okay, that's 1 group, 2 measures. So that's a paired 2 sample looking at the means. Okay, so I'm looking at the group pre to post. And for my group educated, I'm going to say that I think there'll be a difference. I think the group will have a lower blood pressure at the end. Okay, so I'm going to do a directional hypothesis or an alternative hypothesis. So I would drop down then to my one-tailed test. I look at my calculated T statistic of 0.49. It is not larger than my T critical of 1.76. That's backed up with my p-value of 0.31. Okay, so I know that 0.31 is not smaller than 0.05. So there's no difference. There's no difference here between pre and post. Okay, and I know even at a one-tailed test, even when I have a directional hypothesis where all the error is at one level, I still don't see a difference. Okay, so, but if I have a directional hypothesis where I say there'll be a difference, I say, oh, there's going to be a lower blood pressure at post in this group. Well, there wasn't a lower blood pressure at post. Okay, so I would reject my directional hypothesis or my alternative hypothesis that there was a difference. I reject that because there's no difference. Okay, and it's the same on the one-on-one and the passive. There's no difference. So if I did directional hypothesis on each of those, I can look at the one-tailed test. Okay, the calculated T was not larger than the critical T, and this 0.08 is not smaller than 0.05, so there's no difference on the one-on-one group, and then there's also no difference on the passive group. Okay? Okay, so I didn't see any difference in there, in any of those. Okay, so now, today we're going to run the ANOVA. Let's say we want to run a simple ANOVA. We want to see, is there a difference between any of these three groups? Is there a difference between any of these three groups? Okay, so the way we run that, the data has to be in columns right or rows, but they have to be right next to each other. Kind of like when we did the correlation. Remember when we did the correlation? Those two columns of data had to be right next to each other. So, you know, you saw here, I just had them all in one layer. Okay, so it was all in one layer with the group, the one-on-ones, and the passives. Well, we can't do that. We've got to do the groups. We want to look, is there a difference on pre? We'd have to do the group pre, right next to the one-on-one pre, right next to the passive pre. So if we're looking at the difference between this group, this group, this group on pre, we've got to put them all next to each other. Okay? Makes sense? We could also look at it at post. We could put the post mean arterial pressure. We could do the post, the group at post, the one-on-one post, and the passive at post. Okay. The other thing we could do is we could look at so this is three groups, one measure. We could look at one group. We could just look at the passive for pre and post. Okay, but in that case, we could just do a t-test because it's only two measures. Okay, so anyway, to do the ANOVA, we've got our three groups at pre. We've got them right next to each other. So in order to do this, we'd go to our data tab, we go to data analysis, and we're going to go to the single factor ANOVA. Okay, single factor ANOVA. We're going to tell it okay. And then we're going to pull this whole group of data. So we're going to grab the whole group. Okay. I kept the labels in, so I would say label in, and then I tell it where to put it. Okay. So I told it to put it right here in whatever, F15 or whatever. So then I would just say, okay, I've already run this. So this is the outcome for the single factor ANOVA. Okay. So we're going to see the single factor being the pre-measure for the three groups. So the group pre-measure average was 97.125. The one-on-one pre-measure was 105.42, and the passive pre-measure was 97.7. So what it's going to do is it's going to compare these three averages to see if there's a difference. It's going to come up with a between groups and a within groups. Okay? And it's going to give you a F ratio. So our F ratio is 4.75. Our F critical is 3.13. and our p-value is 0.01189. So looking at that, is there a difference somewhere between these three means? What do you guys think? Is there a difference somewhere between those three means? Use your chat and let me know if you think there's a difference. Yes or no? Yes, there's a difference. No, there's no difference. Be brave. Okay, good guess, Jordan. Okay, we don't know that for sure unless we did a post hoc, but there's a pretty good chance that the group and the passive aren't different, but both of them are different than the one-on-one. Okay, but we would have to confirm that with a post hoc test. Excel doesn't do post hoc tests. But like if I put this into SPSS, I can be pretty sure that there would be no difference between the group and the passive at pre, but there would be a difference between those two and the one-on-ones. Okay, so the reason we know there's a difference, okay, so if you're like still tentative and you're like, I'm not sure why there was a difference, I don't really get that. Our calculated F ratio was larger than our critical F ratio. 4.74 is larger than 3.13. So right there, we know there's a difference somewhere. We can double check that with our p-value. Our p-value was 0.01189. That's smaller than 0.05. So 1% is smaller than 5%. So we know there's a difference somewhere. So really, without the post hoc, all I can say is, yeah, there's a difference somewhere. I can do an educated guess like Jordan did and say, I'm thinking that one-on-one group is different, okay? And we can explain this. So in the actual study that we did, we let the participants self-select. So we let them self-select. Would you like to be in the passive education group? So basically, that's our control group. Would you like to be in the control group and not get the education except in kind of just a passive way? Would you like to be in the group where you just come once a month and you get group education? Or would you like to be in the one-on-one where you come one-on-one with an educator and you get one-on-one attention? So we let them self-select into the group. And this was for reducing risk for diabetes and heart disease. So can you imagine, like if we were looking at weights, which we did, we had people with higher weights in the one-on-one group too. So it would be more likely that people with higher risk would select the one-on-one groups because they're probably aware, wow, I have high blood pressure, I'm overweight, or maybe I already have diabetes, or I have I have a little, my A1C is like in a risk range. So those people, we did all the pre-testing and we gave them the results. And then we said to them, which group would you like to be in? And you can imagine the people that were at higher risk selected the one-on-ones. So even at pre, they had a higher blood pressure. Okay. And they were different from the other two groups. Okay, that's not ideal for a research study, but it's the reality. When you're working with human beings, you can't always randomly put them into groups, okay? So because we didn't randomly put them into groups, this was a this was kind of a pseudo experimental study that we did, okay? We didn't have randomization. Okay. Any questions about that? So if this was on a quiz, I would give you the outcome. I would tell you what the F calculated is and the F critical and what the P value was. And you'd have to tell me whether there's a difference somewhere. Then I may give you a Tukey honest significant difference value. Then you could have subtracted these from each other, and if it was the difference was larger than the Tukey HSD, you could have said, yeah, there's a difference. So like I said, you know, let's say we had a Tukey HSD of 4 on this. Well, if we subtract these, the 97.1 and the 97.7, the difference between those is small. So you could say there's no difference. But the difference between this and this, and the difference between this and the difference between the one-on-one and the group, and the difference between the one-on-one and the passive is a difference of about 8 or 7.5. And so you could say, yeah, that's larger than 4. So we know that there's a difference between the group and the one-on-one and the passive in the one-on-one. Okay? So that's what you'll have to do on the actual homework or the test, the quiz. Okay? So it'll ask you questions like that. Okay? So question number 5 on the homework, the question was, was there a significant difference in the 3 groups before? And the answer would have been yes, there was a significant difference between the groups at pre. And then we could look, is there a significant difference at post? So we've got pre. So let's look. I may have the post in here somewhere. Oh, here it is. Okay, so here's my post. So I also looked at, I took their mean arterial pressure, the group post, the one-on-one post, and the passive post. Okay, so at post, the group's mean pressure was 98, the passive's mean pressure was 99, and the one-on-one was 102. Okay, so when we go in here and we run the one-way ANOVA on it, we find that the calculated F was 0.78, the critical F was 3.13, and the p-value was 0.45. So was there a significant difference at post? What do you guys think? Yes or no? Was there significant difference anywhere at post? Was the F calculated larger than the F critical? The F calculated 0.78, that's bigger than 3.13? No, it's not. Is the p-value less than 0.05? No. Okay, so this tells us there's no difference. Remember, for there to be a difference, the F calculated has to be larger than the F critical, and the p-value has to be lower than 0.05. So if you look back at the pre-value, these 3, when we compared these 3, we did get the F was larger, the F calculated was larger than the F critical, and the p-value was smaller than 0.01. So there was a difference here. This was a yes. But when we look at it at post, you can see that the one-on-one blood pressure actually did reduce, but the group pressure and the passive pressure, they actually went up a little bit. At pre, it was like 97 something for the group, and the passive, it was like 97 something. So these pressures actually went up, and the one-on-ones went down. So now there's no difference between the three groups. Okay, so what happened is that we actually saw the one-on-ones reduce. So now, instead of them being different from the other two, having a significantly higher pressure, now they're no different from the other groups. Okay? So if we answer the question was there a significant difference at pre? Thank you, honey. Was there a significant difference at pre? Yeah, there was. We saw that there was a significant difference. Okay? But was there a significant difference at post? No, there was no difference. And then it asked to explain the study overall. So an explanation of the study would be, in the diabetes study, it did not alter the participants' blood pressure overall. Okay. However, the passive group had an increase in blood pressure over the course of the study. And in the increase could, and here's what we determined. We took the pre-blood pressures in January, okay? And we took the post-blood pressures in June, 6 months later, okay? This was done in a warehouse, okay? The workers worked in a warehouse. So what might be different from January to June in a warehouse work setting? Well, temperatures were higher. It was really hot in the warehouse in June. So when we took the blood pressures in January versus in June, people tend to have higher mean arterial pressure in heat. Okay, so that was a factor. That was a confounding variable. That was a variable that changed our blood pressures, our blood pressure measure. Okay, it created error. Okay, so that's what happened. Was we had higher pressures in June. It should have been across everybody, right? Because we measured everybody in the warehouse in January. We measured everybody in the warehouse in June. So higher ambient pressures higher ambient temperature could have caused the higher blood pressures. But the interesting thing is that the one-on-ones actually reduced their blood pressure. We would have thought it would be increased because of the higher temperatures. So what that tells us is that they probably did actually lower their blood pressure. Okay, so the one-on-ones had a higher starting blood pressure than the other groups. This was neutralized by the end, which means that they actually had a decrease in blood pressure. So we had some success with the one-on-ones. They went from being significantly higher at pre to not having any significant difference at post. So that's kind of interesting. Okay. So any questions? If you guys are still struggling a little bit with this, you got to go back in and just practice. Go back in and run these. Write down. If you haven't written this down, write it down. Okay? The calculated statistic must be higher than the critical statistic for there to be a difference. The calculated statistic, so the calculated T or the calculated F, must be higher than the critical T or the critical F for there to be a difference. If the calculated score is higher, you can say there's a difference. Okay? The p-value must be smaller than 0.05 for there to be a difference. If the p-value is smaller than 0.05, you can say there's a difference. Okay? If the T calculated is smaller than the T critical, there's not a difference. If the p-value is larger than 0.05, there's not a difference. Okay? So when you look at that p-value, you can also transfer it into a percentage if that helps you see it better. Is 1% smaller than 5%? Yes, there's a difference here. Okay? Is 45% smaller than 5%? No, there's no difference here. Okay? And these are always going to be congruent. It's not, you're never going to have the F value tell you one thing and the P value tell you something else. They always go together, right? If the P value is higher than 0.05, then the F calculated is going to be lower than the F critical. Okay? Or you could, you know, if it makes it easier for you to remember, if the p-value is higher than 0.05, then the F critical is going to be higher than the F calculated. Okay, they're always going to go together. If the p-value is less than 0.05, the F critical will be less than the F calculated. Okay, so write that down. Okay, because that's the rule, and you have to know that rule to look at to tell whether there's a difference. Remember, when you're running an ANOVA, if it tells you there's a difference, you have to run a post hoc to see where the difference is. So in this case, we would want to run a post hoc to verify the difference here. In this case, will we run a post hoc? No reason to run a post hoc. There's no difference. There's no difference statistically between these three values. They could be considered the same. Okay. Questions? Okay, so my suggestion is, or my encouragement is, you go in and actually do practice homework 7. Go into this data and actually run these tests, these inferential tests yourself. Then you'll look at the inferential statistics, do your rule comparison to tell whether there's a difference or not. Okay, so you're going to be doing the ANOVAs and you're going to be doing the independent and the dependent t-tests. Okay, so you know, you've got to know the rule for whether you do a paired or a 2-sample. Okay, so the paired is the dependent, the within, 1 group, 2 measures. So you should write that down. You got to know that, apply that rule. The 2-sample for equals variances. This is 2 different groups for 1 variable. Okay, so write those down. Those are the things where people tend to get most tripped up, is choosing whether they're going to use a paired or a 2-sample, okay, for the 2 groups. The other place people get tripped up is looking at the outcomes, okay? So they get tripped up a little bit looking at the p-values and the T and F, the T statistic and the F statistic. So write those rules down and then practice them, okay? If you're still feeling confused, go back, watch another video, rewatch this video, okay? Repetition helps us learn. Examples help us learn. Rereading things helps us learn. Re-listening to things helps us learn, okay? So we've got lecture 6 and lecture 7 are on the inferential tests. Those are, you know, your decision-making tests to get your inferential statistics, okay? So what we have left is lecture 8, which talks about how to write the report up. Homework 8, I'm going to go over tomorrow. It's still using inferential statistics, but it's trying to make decisions on what, like program development, or trying to make decisions on what kind of test would be best to use. Okay, so tomorrow we're going to be talking about writing the report up, but we're also going to go through homework 8, which has you comparing a gold standard test, like using the BOD pod over using skin fold analysis, or using max VO2 on a treadmill versus using a step test to figure your max VO2. Okay, so it's using a easier test to predict a test that's much more difficult to calculate. Okay, so we'll be going over homework 8 tomorrow with lecture 8, but they're not really connected. Lecture 8 is just on how to write up your report. Okay, so by tomorrow I'll have the survey completed with your comments. Okay, and then I'll send you the new link, the new URL. Okay, don't use the one I sent initially to send out, because people have found some mistakes, they've made some suggestions, so I'm going to be changing the survey. I will send you the final survey link for you to send out tomorrow. Okay, we got to get those out tomorrow because we've got to get data. Okay, so we've got to get data so we can have something to analyze. All right. Okay, any questions? Okay, so if you have any questions, you can stay on. If not, I look forward to seeing you tomorrow at 10:30 to go over lecture 8 and homework 8 and answer any other questions. Oh, don't forget your discussions are due by the end of the day today. Discussions are due by the end of the day today. Okay, see you later unless you have some questions.
I was wondering if we could maybe go over homework 6 just a little bit, because I didn't do well on it and I thought I understood it well.
Absolutely. So let me do a stop screen share on this, and I will pull up homework 6. Okay. Okay, homework 6. Okay, so let me do a share screen here. Okay, so I'm going to do a share screen on homework 6. So here we go. Okay, so can you see homework 6? Okay,
Yes.
so let me open the data. Okay, so what we were asked to do on this, hang on. Okay, what we were asked to do on this is to, let me look and see what it's asking us to do on this before I start doing it. Okay, so the homework says, open the file attached, complete the quiz by analyzing the relationship between the variables presented in the data using correlation between all the variables. So we've got 3 variables. Oh, we've actually got 4 variables: age, BMI, physical activity score, and percent body fat. Okay, so we're going to analyze the relationship by doing a correlation between all the variables. Then we're going to do a bivariate linear relationship using BMI as the predictor and percent body fat as the predicted. Okay, so let's go in and actually do the analysis. Okay, so let me stop share on this and let me share my Excel. Okay, so can you see my Excel screen now? Okay.
Yeah.
So in order to do a correlation on the on all the variables, I'm going to pull all the data. Oh, not yet. I'm going to do a data analysis, and I'm going to do a correlation. And I'm going to tell it okay. Okay, now I have to pull all the data. Remember, the data has to be in columns next to each other. It could be in rows, but it's kind of easier to have it in columns. So I'm going to pull all this data, and I tell it it's in columns. I pulled my labels in the first row, and I'm going to put this into F1. Okay, so this is now done just a simple correlation. These are all Spearman-R statistics, inferential statistics, okay? So it gives you what the correlation is. So the correlation between age and age is 1 because it's the same variable, right? But the correlation between age and BMI is only 0.07. Okay, so that's a very weak positive correlation, okay? Between age and physical activity score, also a weak correlation. Between age and percent body fat, a little bit higher, but still pretty weak, okay? Between physical activity and BMI, we've got a real weak correlation. Between BMI and percent body fat, it's higher. I wouldn't say it's strong, but it's higher, right? And then physical activity and percent body fat, weak, 0.09. Okay, so probably your best correlation here is the 0.48 between BMI and percent body fat. It's not super high. Like if it was above 0.7 or above 0.8, I'd be feeling really good about it. But I'm not feeling super great about it. But I can go ahead and run a regression on it just to see if it's significant. Okay, so out of all of this, the one that I'm most likely to run the regression on is the highest one, right? The one that has the strongest correlation between BMI and percent body fat. So that's what the homework asks us to do. It says, do a linear regression using the BMI as the predictor variable and the percent body fat as the predicted variable. Okay, so in order to do the regression, I'm going to go back to data analysis. I'm going to go to regression, tell it okay. Okay, now my Y range, the homework told me my Y range is the percent body fat. That's what I want to predict, is their percent body fat. So I'm going to pull the percent body fat for my Y range. And then my X range was the BMI. So then I'm going to pull my BMI. Okay. So I've got my two ranges. I had my labels in there. Okay. I can tell it that I want a 95% confidence level. Okay. I'm going to tell it to put it in F10. And then I'm going to go ahead and do, I'm going to go ahead and do a line fit with that, a line fit plot with that. Okay. Okay, so here's my output. Okay, I knew that the regression, I know that my correlation was this 0.482799. So there it is. Okay, it explains 23% of the variance. Okay, and then I know my standard error is 7.21. So there's a lot of error there. Okay, because remember, this is plus or minus 2 times this number. So this is 14.4 plus and 14.4 minus. So it's a variability of 28%.
So like on the homework, I put the 7.21. Would that have been wrong because it had to be the 14?
Yeah, because you remember there's two standard deviations, not just one. You're going to add it once and then you're going to add it
Oh,
again, right? So that's a really common mistake
well,
that
I
gets
did it
made.
like twice, so I think like, I
Yeah.
don't know where I necessarily like messed up on that.
Okay, well, we'll go back and we'll look at the questions, okay? So here's the plot. So you kind of see where that line of best fit would lie,
Mhm.
okay? Then we go in and we look at the outcomes. So here's the F statistic, okay? And, oh, it's not, because I said 95%, it didn't give me the F critical. If I wouldn't have put the 95%, it would have put the F critical here. It's just telling me the p-value.
But then the p-value would show that it's not significant. Or
Okay,
no,
so
it would.
look at, remember this is to the negative 0.06, so I'm going to move my decimal point 6 points this way. So it's going to be 0.50575. So is it significant?
Yes.
Yes. Okay. So if I wouldn't have put that 95%, it would have given you your F critical, which was lower than your F calculated. So you probably saw that because you probably didn't put the significance. Okay. Okay. So then it's also giving you your intercept. Okay. And it's giving you your slope. Okay. And then it also gave me my residual outputs because I asked for it to get the line of best fit. Okay, so let's go now to the homework. Okay, so let me stop this share. Okay, so any questions on this, on how to get this? Did you feel like you got the right, did you do it right? Did you,
I have it pulled up on my screen. Yeah, I
did
don't know.
did it give you the F critical?
No, I put the 95%
Oh,
in.
okay. Okay. So let's do it. You know what? Let's just run it without the 95%. And let's see, where should I put this though? Let me put this in, N1. Okay, let me just move this. Okay, so if I look at this, oh, it's not giving me the, okay, but you're still seeing the difference. Okay, the difference, because this is the p-value that we're looking at. Okay, so let's go back to, let me stop the share and let's go back to the homework in Blackboard. Okay, so can you see the homework now?
Mm-hmm.
Okay, so here's the questions. Okay, so which two variables had the strongest relationship? The BMI and the percent fat, right? They had the strongest relationship. It was the 0.48, right? So if you went to the correlation, this was the strongest relationship. Okay, are you seeing that? Okay. Okay, then it asked, was this a positive, direct positive or an indirect negative? Okay, well, you knew it was positive by looking at the simple correlation. So do you have your simple correlation up, Sierra?
Well, that's I think what kind of confused me was because I didn't think it was like significant, so then I put non-directional because I didn't think it was like direct.
Okay, but remember, okay, let me actually go back real quick. Remember that when you're looking at positive versus negative or the direct versus indirect, that's just all like if we look at this, if this is a positive 0.07, this is a very weak positive direct correlation because it's a positive. This is a very weak negative or indirect correlation.
So will it ever be non-directional then, or is that not a thing?
No, that was just something to throw people off that didn't know what they're talking about. Okay, so it's either going to be positive, these are all positive correlations, positive and direct, or it's going to be negative.
Okay.
Okay, so I mean, this is weak, but this is a weak correlation that says as your physical activity scores go up, your percent body fat goes down. Okay, it's very weak, but it's still a weak indirect correlation.
Okay.
As one goes up, the other one goes down. Where this is a, say for instance, this is a weak positive correlation. As your age goes up, your BMI goes up. There's a weak positive correlation.
Okay.
Okay, does that make sense?
Mm-hmm.
Okay, so so if we go back to the test, that was a direct or positive correlation. Okay, even though it wasn't super strong, it was still positive. Okay, but it was way stronger than the other ones, right?
Mm-hmm.
And when we look at it, the relationship between BMI as the predictor variable and body fat as the predicted variable, it's a direct relationship, a direct correlation, and it was statistically significant. So that it was, you know, the outcome was less than 0.05, right? The probability was less than 0.05. So it was statistically significant, and it was a direct correlation.
For the BMI and body fat?
Yes.
Because I got or on my correlation, I got 0.48.
Yes. So that's direct and positive, right?
Mm-hmm. I just thought it
So
had to be like, I thought you said if it had to be like 0.78 or like 0.7 or zero point 0.8 for it to be like considered like
good,
significant.
really strong. But
Mm-hmm.
when we ran the regression, we found out that even
Like a
though it
positive,
wasn't
or
super
okay.
strong, it still was significant.
Okay, I get it.
Yeah. So if you have a lot of data, like, you know, we had we had 80 observations, so we had a lot of data. We had a lot of power. So with that additional power, it actually became significant.
Okay, I see.
If we would have only had 20 data points, it might not have been significant. So the larger your group and the larger your power, the more likely you are to pick up on the significance.
Okay.
Okay, this actually was statistically significant, and it's a direct correlation.
Okay, yeah. I was just looking at the correlation and I didn't look at the regression when I was doing that.
Yeah, so you definitely, to see if there's a statistical significance, you've got to look at the outcome of the regression, right?
Okay.
And then if you were to make an equation, y equals the slope. So let's go back. Let me go back really quick to the outcome. So if we're looking at we go down here to our outcomes, y equals the slope, right? Which is the 0.57 times x plus the intercept, which was 9.55. Okay, so the best answer there was the y equals 0.576037 times x plus the intercept, 9.552398.
Okay.
Do you see, is that one pretty straightforward?
Mm-hmm.
Okay, so always remember, this is the slope for your variable, for your independent variable of BMI. That's where you're going to find your slope. And then your intercept is right above it.
Okay.
Okay. The next question is it reasonable, is a reasonable interpretation of your statistical calculation to say that, and then it was it was like increased physical activity causes decreased BMI? Increased body fat can accurately predict with reasonable error from BMI? Percent body fat is significantly related to BMI? And increased body fat causes increased BMI. Okay, so the best answer there is that there's a relationship. Okay, there's a relationship. Okay, we did do a prediction equation, but because the error rating was so high, because it wasn't that the correlation wasn't above 0.7, I'm not sure how accurate your equation is going to be.
Okay.
Okay, because when you drop down, your error rating was the 7.21 times 2. So it's plus or minus the 14.42. That's a really common mistake. That's another write down thing. You always have to multiply the standard error times 2. So it's plus or minus 2 times the standard error.
For the 95%.
For the 95%. If you were at 99%, what would you do?
I know it adds like 0.24.
Yeah, but if I'm doing 2 times the standard error for the 95th percentile, what would I do? The 99th percentile is 3 standard deviations, right?
So the 7.21 times 3?
Yes, times 3 plus or minus. Okay, so if you're in the 95th confidence interval, it's 2 times the standard error plus 2 times the standard error minus, right?
Okay.
If you're in the 99th percentile, it's 3 times the standard error plus 3 times the standard error minus. So you can see there's tons of error. There's 28.84% error if you look at the whole 95th percentile. That's why you can't really say that it will accurately predict BMI. It'll predict it within 28%. That's pretty broad, right? That's a lot of error.
Yeah. Mm-hmm.
So the best thing you can, the best interpretation you can go for, let me go back to the questions. The best interpretation you can go for the study is to say that percent body fat is significantly related to BMI. We saw that from the regression. There was a significant relationship, but I'm not sure that we feel good because the error was so dang high. I wouldn't have chosen this one.
Okay.
Okay, does that make sense?
Mm-hmm.
Okay, so always, if you're going to do correlation, if you want to do a regression, just choose the highest correlation. If you have a lot of data, it might be significant. But if there's tons of error, I probably wouldn't use it. Okay. Right? So then that's why you want to look at your standard error. Okay, you can only say, hey, there's a significant relationship between the two, but I'm not sure it's high enough to do a prediction.
Okay.
Okay?
Okay, thank you so much for going over that.
No worries at all. Courtney, did you have any questions?
No, I just wanted to go over that as well, but then I was also just wanting to check with you about my emails and just making sure that they're going through.
Have I, the ones that I've gotten, I've responded to.
Okay. Because I just wanted to make sure that you'd gotten like the ones where I sent like the links to you in regards to the score that we were trying to find, like the score table that you were wanting, and then a research article about the sexual education.
Yeah, and I would really love if you would post those links to the discussion. Did you do
Okay.
that?
I don't think so, not yet.
Yeah, so I had sent
I
an
looked.
email about that saying, really important for you to post your links to the discussion board because that's really where I'm going to grade from.
Okay.
Because then they'll be all in one place. Since people had found more, then just post them all there on your on a thread for the discussion board.
Okay, I just want to make sure you're getting them,
Yeah,
but I'll do that. And
yeah.
then I didn't know if you'd gotten the one about the survey monkey from
Um,
earlier.
do you know when you sent that?
I sent it early this morning.
Let me look really quick. Yes, I did get it.
Okay.
So I will, and I actually had gotten about 5 of them this morning. So I'll have that marked down for your grade.
Okay. I just wanted to make sure as far as like grade goes that everything's being submitted and you're getting everything that you need from me.
Right. Yeah, I think we're good.
Okay. Right.
Okay,
Well,
great.
thank you. Have a good day.
You bet. I'll see you tomorrow.
See you tomorrow.
Bye-bye.